Hello, everybody. Just waiting for my computer to catch up. Not sure if it's actually going live. Oh, there we are now. Excellent. All right. So, um, today we're going to talk Year 12 chemistry. So, this, if you're Year 11, you can watch on, and this will be coming up later in the year for you. Otherwise, if you're Year 12 and you're struggling a little bit with stoichiometry, I'm just going to have a little refresher on stoichiometry, and then talk about limiting reactants because that's what's happening this year. So just let me share my screen with you. Give me 1 second. I'll find my presentation. Make it a slideshow. Excellent. Okay, so let me just make sure all of my other bits and pieces are in order. Okay. Just so that I can see if you are doing any comments, giving me any comments. All right, so excellent. Hopefully I should see the comments if you make a comment. All right, so let's have a look at stoichiometry. Now, a lot of students get a little bit scared or they get a bit confused by stoichiometry when you just have to, we're so used to using the properties or the values of mass and volume. That's second nature to you when you're, thinking about doing calculations or looking at things. You've got volumes of things in the kitchen and masses when you're cooking. They're really, really common measurements. Now, the mole is slightly different in that it's counting particles. Now, we do that because in your chemical equation, you have two of these react with one of those to create three of those and four of those. I don't know, whatever the equation might be. So we're actually counting numbers of particles. It doesn't matter how much those particles weigh. We have to take that into consideration when we're doing our calculations. But it doesn't matter how much those particles weigh when we're working out how much. Yeah, so that's why we can't just use direct masses in our equations. We have to use number of mole. Now, of course, the number that we use a lot in everyday life is the dozen. And I'm 100% certain I can hear your teachers saying, oh, how many is in a dozen? Well, 12. If I've got 3 dozen, how many rolls have I got or how many eggs have I got? You just know that because it's a value that you've used a lot. The mole is no different to that. It's, okay, I've got a mole of molecules and it stands for this number here, 6.02 times 10 to the 23. Now, if we were to expand that, it's like 602,000, massive number, massive number. And the reason it's a massive number is because molecules are so small. Can you imagine trying to do the maths without a unit like the mole? You're going to have enormous numbers that you've got to try and calculate your answers for. So the mole is really, really handy because it gives us manageable numbers to do our calculations because we're looking at huge, huge numbers. Yeah. So think counting particles, masses can be different. Yeah, they can weigh different amounts because it depends on what is in that molecule or even the atom as to how much it weighs. So the masses are going to be different. We can't relate them directly through mass. We have to go through the mole. Okay. And as you know, we relate this to the kitchen all the time. If you are adding in a recipe and really fiddly things like souffles, you need to have exactly the right amount. If you don't have the right amount, you'll have a pancake and not a souffle. And stoichiometry is exactly the same. Now, we use it because, in industrial chemistry, they're not just going to throw buckets of chemicals in there and just hope for the best. They're going to know exactly how much of each reactant they need to produce a certain amount of product so that then, it's all about money, so that they can produce the products they required. And when we move on to area of study 2 and unit 4, you'll see that there's more to consider in that kind of scenario. But that is what we're looking at. We're looking at, I'm putting in a certain amount, how much am I going to get at the end? Yeah. So it's the same, chemical reactions are the same as a recipe, essentially, in the kitchen. All right, so there's a lot of information that we can gain out of our chemical equation. Now, usually your chemical equations at year 12 should have states, so you'd know what state those substances will be in. You know that you need 2 hydrogen molecules to react with 1 oxygen, or we can say 2 moles of hydrogen, so 2 times 6.02 times 10 to the 23, plus 1 mole, which is just 6.02 times 10 to the 23, will react and produce 2 moles of water. Okay, so there's lots of information you can get just from the reaction. And now that you're in your year 12, you'll have a delta H, which tells you the amount of energy that's released. Remember, when we're talking about energy, we did this a few weeks ago, that 2 moles of hydrogen will produce a certain amount of energy that's associated with that equation. Okay, there are a few things that a reaction doesn't tell you. Now, it doesn't tell you anything about rate. So it could be super slow, it could be really fast. It doesn't tell you anything about how fast the reaction is going to go. The second thing is, if you don't have the delta H value attached, it doesn't tell you if energy is required or given off or anything like that. It doesn't tell you anything about energy, and it doesn't tell you how individual atoms or molecules are transformed. Yeah. One of the best reactions for that is, this year at year 12, you need to know about photosynthesis and cellular respiration. When we look at the photosynthesis reaction, which you should know, by the way, it just looks like carbon dioxide and water produces glucose and oxygen. Yeah, photosynthesis. But actually, if you do biology, you'll know this. It happens in 2 different spots. It's a very complex biochemical pathway. But as chemists, we like to simplify everything down and look at what goes in, what comes out, and cancel out anything that's kind of there at the end, so that we just have a really simple equation. So it doesn't actually, the reaction doesn't tell you how this all happens. It just tells you that this will become that. But it might go through 3 or 4 different steps. Who knows? In a biochemical pathway, it often does. In a chemical reaction, sometimes you've got intermediate steps. Absolutely. All right, so now that you know about energy from the start of the year, you can also include, because you should have done some stoichiometry last year, you can also include some stoichiometry according to your delta H. And I'm going to talk to you about that. I've got a question at the very end of this presentation. But the formulas that you need is number of moles equals CV, number of moles equals mass over molar mass, and controversially, PV equals nRT. The other one could be number of moles equals V on Vm, so volume over molar volume. That also is a good one for gases. You'll need to know about mole ratios and obviously your enthalpy changes if required for that question. So let's just really recap really quickly, because I'm going to talk about limiting reactants, and that's new this year. You should know about stoichiometry from last year a little bit, so let's have a little refresher. So first, we have to write a balanced equation. We can't do any maths until we know exactly what's going on. So you need a balanced equation. Don't forget to balance it, okay? I've seen lots of students write fantastic equations, worked it out brilliantly, then forgot to balance them. So make sure it's balanced. Then you're going to calculate the number of moles of something. Like literally, this is what I say to my students all the time. Your very first step is always calculate the number of moles of something. You will have enough information to do that in your question. All right. So whatever you calculate the number of moles of it. Then we're going to use our mole ratios to find our target molecule. So whether that's you've got enough information about a reactant, and then you want to know about how much you're going to produce, you're going to use your mole ratios to head in that direction and then find your answer. Now, that might be find a volume, it might be find a mass, depends on what your question is asking. But the first 3 steps are always the same in stoichiometry pretty much. Write a balanced equation, find the number of moles of something, and then use your mole ratios to go to where you need to go in your question. Okay, so here's an example. I've got a pretty complex equation there. Phosphorus may be prepared from calcium phosphate according to the equation above. How much phosphorus can be produced if 1,000 kilograms of calcium phosphate is used completely? All right. Now, that might not seem like much. We've only got one value, but it's a mass. And you've got a periodic table, and so we can work out mass the number of moles by working out mass over molar mass. All right, so calcium phosphate, let's identify what that is. That's this thing here. So I'm going to calculate the number of moles of something, which is this. Then I'm going to use my mole ratios to find phosphorus, which is this one over here, P4. So I'm going to calculate my number of moles, divide by 2, because I'm going to divide by 2, multiply by where I'm going, and I'm going to times it by 1. Don't really need to do that. Divide by 2, times by 1, and then I'm going to find the mass. And that looks like that. So calculate the number of moles of something, mass over molar mass, then mole ratio, and then mass equals number of moles times molar mass. Now, see how we've used the same equation twice, just rearranged slightly. I have not, even though I've been given a mass here of calcium phosphate, I haven't related that directly to my mass of phosphorus there because, you know, it's mass. I'm trying to find a mass, all masses, but remember they weigh different amounts. Calcium, like calcium phosphate has oxygen, it has calcium in there that's contributing to the mass. This phosphorus over here is just phosphorus. Okay, so that's the only thing contributing to the mass. So you can't relate them just with mass values. You have to go through number of moles because we know that 2 calcium phosphate molecules will produce 1 phosphorus molecule. Yeah, so you have to go through the number of moles. We're counting particles. Yeah. All right, limiting reactants. So this is where you recognize this by you have too much information, okay? Too much information. And you can calculate the number of moles of more than one thing, yeah? So an example is, you know, you have an ice cream sundae, for example. What we're looking for is what's going to run out first. And that's the thing that's going to limit your reaction, because once that's run out, it's not proceeding any further. It's not going to keep going because they've run out of a reactant. It's like making the ice cream sundae. if you've got, you know, it takes 2 scoops, a cherry, and 50 mils of syrup to make this sundae. Here, I've got 8 scoops of ice cream, I've got 6 cherries, and I've got 2 portions of my chocolate syrup. Just as a guess, what am I going to run out of first? My chocolate syrup there, yeah. So I'm only going to make 2 because the chocolate syrup is going to run out. I can't make a sundae if I've got not enough reactants. Exactly the same for your equations there, yeah. So, for example, if you've got this equation here, you have 10 ethane molecules and 100 oxygen molecules. So this is not moles. Could be, but it's not. This question is just molecules, which is limiting. All right, so we can simplify it. So for this one, because it's just molecules, we can simplify it down. So it goes from divide both by 5, essentially, and we've got 2 ethane molecules and 20 oxygen. So ethane ends up being your limiting reactant. But what you would do is say, okay, I've got 10 ethane molecules. I'm going to divide it by 2, multiply it by 7, okay? And that is going to tell me that I'm going to require, so what is that? 10 divided by 2, which is 5, times 7 is 35. I'm going to need 35 oxygen molecules to react with that. I've got 100. So oxygen is well in excess. All right, so let's look at a strategy for our limiting reactants. So I'm going to write a balanced equation. That hasn't changed. I always need that balanced equation. Then I'm going to calculate the number of moles of the known substances. So there will be 2. There may even be 3. That'd be a bit mean, but they will definitely be 2. You can calculate the number of moles of 2 things, yeah? What you need to find is which one is going to run out first. So when we find the limiting reactant, we use our mole ratios. So you've got, say, you find the number of moles of A and the number of moles of B. They're your 2 reactants. I'm going to then divide my number of moles of A by the coefficients that is in front of A, yeah? So that might be 2, for example. And then I'm going to take my reagent B that I've also found the number of moles of, and I'm going to divide it by its coefficient. So the coefficient of B, yeah? All right, and I'm going to choose the smallest number. That smallest number is my limiting reactant, okay? And you can double check it the way that I did in that equation before. If I divide it by the coefficient of what I have, multiply by the other one, that's how much I need to react with that. If I've got that, then it is limiting reactant. If I don't have it, then it's in excess and I have to use the other value. You could do that as a double check if you're not sure. But as long as you work out the number of moles of both and divide by their coefficients, yeah, in the reaction, then you choose the smallest number. That's the limiting reactant. So now that's just the step in the middle for limiting reactants. You found the one that's going to run out first. So that's the one that will run out. So we use that one to calculate whatever your question is asking, something to do with products, perhaps. Yeah. So relate the number of moles of that to one of your products then. Okay. Excellent. And then once you've calculated that, obviously you might want a moles or mass or a volume or something of your product. So you find your answer. Yeah. Now, remember, there will be something in excess. Now, this is really important, especially if you've got, say, a gaseous equation, perhaps, or something like that. Remember, there's always something left over. So if your question asks something like, how many moles of gaseous substances is left over, you have to calculate the number of moles of gaseous products, and you have to calculate how much is left over, yeah, of your excess reactant. All right. Shoot me a question, an email, or if you want to go through that. Let's have a look at just how this actually works through a question. Okay. So I've got this question. A solution containing 8 grams of silver nitrate is mixed with a solution containing 8 grams of barium chloride. Calculate the mass of silver chloride precipitate that will be formed. Now, in this question, really handy, they're both masses. So I can use number of moles equals mass over molar mass for both. But they may have given me 8 grams of silver nitrate and then a concentration and a volume of the other reactant. Absolutely fine. You need to know all of those equations. So look at what you've got, tag your information on your equation, and then we can go from there. So write a balanced equation and tag that information. So you can see here I put 8 grams there, 8 grams there. Perfect. Now, too much information. I've got to work out the number of moles of both of those things. So I've done that, calculated the number of moles, and by the looks of things, silver nitrate is in excess, but no, we have to divide by our coefficients, remember? So if we find a limiting reaction by dividing by our coefficients, so my silver nitrate here, I'm dividing that by 2, and my barium chloride, I'm dividing that by 1, because remember, it's the coefficient of the substance you're looking at. So now my silver nitrate has become my limiting reactant, yeah? Because it's the smallest number. All right, so now what I'm going to do is I'm going to use that value to then calculate, what am I calculating? Silver chloride, the product there, silver chloride. All right, so now I'm going to use that silver nitrate. I'm going to use my mole ratios in the equation, and once you get used to your stoichiometry, you can see that this is a 2-to-2 ratio, so it's exactly the same number of moles. A lot of students find that hard to get their head around too, because we're talking about numbers of things, remember? So number of moles of silver nitrate is going to be the same because their ratio is the same. It's 2-to-2. So, but if you wanted to divide by where you are, multiply by where you're going as a procedure, absolutely fine too. So it's divide by 2, multiply by 2, same value. And then we can find our mass of using our limiting reactant. What I could also ask is how much barium chloride is left over. And so what I need to do there is go back. I'm just going back. All right, so I've got 0.0235 moles with my limiting reactant. But I can even go back even further and go, okay, well, I know that silver nitrate's I know that's limiting. My number of moles is here, but way back at the start, 0.047. Then I can divide by 2, multiply by 1, and that's how much barium chloride I'm going to need. Yeah, I'm going to need essentially 0.0235. I know I've got 0.038, so I can just subtract that number. Yeah. So shoot me an email if you need to have a look at that a little further, or write a comment in the comments. Absolutely, I can answer that for you if you've got any trouble there. All right, so that's our stoichiometry refresher for this tonight, and with our limiting reactants. I do have one question here that involves energy. Now, I haven't gone through energy with you tonight. I just wanted to kind of do that refresher because some students still, haven't got a handle on that, but also it's really good to have a refresher before you go into class, perhaps. This one involves energy, and hopefully you've been looking at some of these calculations anyway in the energy unit. So let's have a look. The molar heat of combustion of pentanediol is 3,329 kilojoules per mole. Okay, so every 1 mole, it releases 3,329 kilojoules. Okay, we've got a molar mass, means we might need to calculate something there. And then the mass of pentanediol in tons required to produce 10,800 megajoules of energy is closest to. All right, have a little think. I'm going to give you a couple of seconds. If you're watching after the fact, pause and have a bit of a think at how you might do this one, and then we'll have a look at the answer and go through it together. Where will you start? We don't have a mass, even though we've got a molar mass. But something we do have is kilojoules per mole. Okay. And I need a mass. All right, so let's have a look at the answers. So down here, we have 10,800 times 10 to the 3 kilojoules, because this is in megajoules. Remember, you need to be able to convert your units really easily. So we can make that value, megajoules into kilojoules, divided by 3,329 kilojoules, because that's how much energy is in 1 mole. And that gives you the number of moles that produces that amount of energy. Okay? And so then, now we have a mole value. We can use our number of moles equals mass over molar mass, rearranged to find a mass. So remember, we've got number of moles times molar mass gives you that, and it's in grams. Okay, so now the conversions come through again. So we need to make sure that it's 285, 285 kilograms, but they want it in tons. So we're going to divide that by 1,000 again. Okay. Now, another tip, just one tip before I go about converting units. So when you're converting units, if your unit is getting bigger, so for example, like kilojoules and megajoules is bigger, it's a bigger unit, your number has to get smaller. So if you're confused and you just in the moment get confused about am I multiplying or dividing, which way do I go? Just have a think, all right, I'm going from kilojoules to megajoules. That unit is bigger, it's a bigger unit. So my number has to get smaller. So I must have to divide by 1,000, not multiply by 1,000. And you can think about it, try and think about a unit for example, meters and kilometers. All right, a kilometer, the unit is bigger, yeah? So if I've got 1,000 meters and I want to convert it into kilometers, I'm going to divide by 1,000. So it's 1 kilometer. Yeah? So my number gets smaller, but my unit gets bigger. Does that make sense? All right. So that's all I have for you tonight. Please let me know via email. Even if this is helpful, write a comment there. That would be fantastic. If you would like to see something in particular, I'm more than happy to run a session on anything that you might be having trouble with, anything you might want clarification on. Just let me know. All right. I'll see you next time.